Howdy, y'alls. It's the via. I can't speak today. Howdy, y'alls. It's the Diabolic Bee Tutor. And you know what time is it? It's Trig o'clock. So, here we are again. Continuing from last time's stream where we were doing the trig properties. It was the, what was it called again? The expansion, the sum difference expansion identity property. So we did a fair number of those types of problems, and then now we're going to be working on the converse. Is it the converse? I guess it's just going backwards. I'll just say it informally, going backwards for the sum difference identity property for the trig functions, specifically sine, cosine, and tangent. We're going to do some review problems from last time, and then we are going to do some different type of problems, but in all honesty, they're pretty much the same thing, right? And of course, covering the quote-unquote going backwards type of problems. So let us get started. Again, starting off with the review type of problems. Alright. So first off, we have the sine function. Sine of what? It's going to be 59 pi over 12. There it is. And let me check something real quick. Oh, the properties are all gone. That's okay. So here it is, and we have a number of ways of going about doing this, but make sure you check to see if you can simplify this, because this is dredging up one of those older ideas that we can have potentially coterminal angles, and then if you are dealing with a coterminal angle, please reduce it to the smallest positive or the smallest negative in terms of size, so that it's something more easily recognizable. So here again we have the 59 pi over 12. In order to have full circle, what is it again for full circle? It's going to be a total of 2 pi. So for every 2 pi that we get in terms of the angle, that's going to be something that we can reduce to make the numbers slightly better. Not tremendously better, but just slightly better. So, for example, if you had something, if we were doing a problem like 7 pi over 3, this is a separate problem. So suppose we're doing something like this one, you can see that 7 is more than twice of 3. So what we can do is we can split this up into a singular pi, 1 pi, and then plus 6 pi. Because again, the 7 has multiple 3's that you can divide out from it. You can split the 7 into 1 plus 6, and then this one is the reducible one, so therefore what we have left over is just a simple pi. So the problem pretty much devolves into sine of just pi. So that's the, pi over 3, I'm sorry, pi over 3. I forgot this is called partial fraction cancellation, which is illegal, so don't ever do that. That's very sloppy of me. Let me backtrack just a little bit. So again, working like this one, we can decompose the fraction. Fraction decomposition number 1 becomes pi over 3, and then fraction term number 2 is 6 pi over 3, which is 2 pi. So this part is the excessive part. You can simplify it into just pi over 3, so therefore this problem, you can transform it into sine of pi over 3. And then just resolve it from there. So weeding out the coterminal angles first, simplifying it to make the numbers a little nicer, and then hopefully the problem becomes a little easier. So dealing with this one, we can transform the 59, because 59 is more than twice of 12, right? So there are various ways we can go about doing this. I'm just going to think about it as 12 times 4 is 48. Because again, 48 pi over 12. If you simplify that, then you are going to get 4 pi, which is simplifiable. So therefore, all we need to do is subtract the 48 pi from the 59 pi, thereby getting 11 pi. So thus we can decompose the 59 pi into this nonsense right there. And then we could further deal with this one. But let's first just chop off that little part right there that we don't need anymore. So decomposing the fraction, we're going to get 11 pi over 12, and then plus, again, 48 pi over 12 simplifies into 4 pi. And again, this one is just spinning extra rotations. 2 full rotations are extra spin, so we don't need this one. Chop it off, and this is the coterminal angle, the most reduced positive answer that corresponds to that angle. Alright. So now that we have the 11 pi over 12, this one is the quote-unquote nasty denominator. We need to change it into like a 4, a 3, or a 6, or a 2, and that would be the optimal situation. So this one, we need to bust out the property. All we need to do is just split up the 11 pi. So how can we split it up into a situation where the numbers are nice? Well, let's think about it for a moment. So splitting up the 11 such that we can get some sort of simplifications potentially with the 12 on the bottom if we decompose the fraction. So what can we split the 11 into? We could split it up into what? 3 and 8? Yep, that looks pretty good. Because if we split the 11 into 3 plus 8, if we decompose the fraction, we're going to get 3 pi over 12 for fraction number 1, and then fraction number 2, we're going to get 2 pi over 3. And then this one is simplifiable, and then this one is... Wait, I already simplified. I automatically simplified. Whoops. Why did I do that? Okay. So that simplifies in... Before we simplify it, I should say. So we can decompose this fraction into these two, and then we can carry out simplification. Pi over 4 is a nicely recognizable special right triangle angle, and then this one is also a nice one. Top and bottom divided by 4 becomes 2 over 3. 2 pi over 3. So that's nice. That's a 45, 45, 90 situation, and then this one is a 30, 60, 90 situation. So this is a good split for the 11 pi, but there are other splits that we can perform. We can perform the 2 plus 9 split as well. And again, just checking the decomposed fraction, we're going to get 2 over 12. 2 pi over 12, and then plus the 9 pi over 12. Those two fractions are also simplifiable, thereby getting a pi over 6, and then a 3 pi over 4. So we have a couple of roots, root number 1, root number 2. I'm sure there are other roots as well. I'll leave that up to you for investigations if you wish, but in all honesty, you're going to end up with the same thing, right? Hopefully. So I'm just going to work with, let's work with this one. So arbitrarily, I'm going to delete that one, and I'm just going to work with the 3 plus 8 split. So I will arbitrarily choose to decompose this singular angle into angle number 1 plus angle number 2, and then simplifying it to this one, and then thereby allowing us to do the setup. So sum difference formula, we're going to split this angle into 2. It's going to be this one and this one. And the formula for the sine function is to do the sine, cosine, cosine, sine. It's not cosine, so you don't keep the sines together, nor do you keep the cosines together. But sine will maintain the same sign. So since we're doing a plus, it's going to be sine, cosine, plus cosine, sine. Just following the algorithm, nothing particularly spectacular. So this is going to be angle number 1, pi over 4, and then we put it right here as well, pi over 4, following algorithm, and then angle number 2, the term number 2 of the argument is going to be 2 pi over 3, and then 2 pi over 3. So that's argument number, that's term number 1 of the argument, and this is term number 2 of the argument. Follows this exact same form. That plus came from the plus because we're doing the sign. You keep the same signs. Alright. Sketch out the triangles, the reference triangles. So this one's going to be the 40, 60, 45, 45, 90 in the quadrant 1. The ratio is 1 to 1 to root 2. And then this one is going to be the 30, 60, 90 with the 60 as the reference angle, and it's going to be in the second quadrant because 2 is 1 short of 3. So we're looking at this particular triangle with a negative 1 to positive root 3 to positive 2 for the ratios. Alright. The reference triangles are sketched out. Now all we need to do is evaluate. So sine of this one is opposite over hypotenuse. So root 2 over 2. This one right here is adjacent over hypotenuse. So times in the parenthetical. So don't, again, from previous warnings, don't just write it like this because it looks like a subtraction thing. This is a product. So parentheticals are pretty nice. Make good use of those ones. Let's copy paste the plus. Cosine of pi over 4, same as the first one. So root 2 over 2. Sine is opposite over hypotenuse. And then we should be good to go. So this one transforms into root 6 all over 4 because this denominator will match this one. I'm just going to combine them in one swift stroke. This one is negative root 2. And then we're done with this particular problem. Good to go. I'm not going to go over the alt root because that's not the main emphasis for today. But you can go over it. I think it's a good exercise. So we have cosine of 75 degrees. Mixing it up. So now we're going back to good old degrees. So not just radians. We also have degrees. But you're going to start to recognize these numbers as well. Because honestly, all you're trying to do is you're trying to get the very nice angles. You're trying to get the 30 degrees. You're trying to get the 45 degrees. You're trying to get the 60 degrees. Or one of the interquadrant angles. It could be 0. It could be 90. Etc. Etc. Right? So you just want these nice angles. What can we do from this one? Well, the closest ones, 30 and 45. So already we can come up with the split for that one. So 30 degrees plus 45 degrees. We can do that as a sum. Alright. So using our cosine, remember you keep your trig type functions together. So the cosines are together because co is like cooperate or coordinate or company. You keep them together. So cosine, you don't keep the same sign because this is the cosine, not the sine function. So you don't keep the same sign. So this positive now, negative. And then we have the sine times sine. And just following algorithm. I should write the angles first, honestly, just for clarity, but I just like to proceed in this particular fashion. So this is going to be 30 and 45, 30 and 45, 30 and 45. So there we go with the expansion. This one is a 30 degrees. That's in quadrant 1. We're referencing the slim angle right here. Opens up to 1 to 2 to root 3 ratios. And then this is the 45 in quadrant 1 as well. 1 to 1 to root 2. Not too bad. Cosine, root 3 over 2. And cosine of 45 degrees, root 2 over 2. Copy paste, copy paste. Sine of 30 is opposite over hypotenuse, so 1/2, and then the 45 back to here, root 2 over 2. And of course, carrying out the operation, this is going to be, common denominator is 4, and then this is root 6 minus root 2. All over common denominator is 4. And then we're good to go with this particular problem. So is this the only split that you can perform? No. There's going to be some other potential splits you can do, but honestly, I just like this one because the numbers are smaller. Alright, next problem up we have sine. It's going to be a negative angle, and we have, no, not negative, I'm sorry. I can't even read it. 17 pi over 12. So this ain't going to be one of those coterminal angles, because if you double 12, it's 24, and this is less than 24, so there's no need for simplification in that particular manner. But we do need to split this one, so we could just jump straight to the expansion, because the 12 is not a nice denominator, quote unquote. It needs to be, again, it needs to be a 2, or a 3, or a 4, or a 6. This is a 12. So how can we split this up? Well, 17, well, we need something that has a factor in common with 12, and the other thing on top of there needs to have a common factor with 12. This could be plus or minus. So what do we need? 17 can split into, don't pick 5 and 12, for example, because 5 doesn't share a factor with 12. So that's a losing strat, because if you do it like this one ends up being nice, but then this one, it's not very nice. You would have to further do some more expansions. Yeah, you could do expansion. Actually, you know what? This might actually be interesting. Let's consider this pathway. So 17, you can decide to split it up into 5 and 12, which, in my opinion, isn't the most optimal strat, but you can do it. So this one is nice, again, but this one is not very nice. But just for sake of illustration, let's do it this way. Alright. So what happens if we split it up in this particular fashion? This one can't simplify, but this one we can simplify. Alright, there it is, and then we have the sine function, so this is going to be sine, cosine, cosine, sine. And since we're doing sum, then sine keeps the same sign. I'll stop saying that so much a little later. So angle number 1 is going to be that nastiness, unfortunately. It's the consequences of our actions. And then that one there, and then that one there, right? Just basic following the algorithm. So that one we can evaluate, and then this one we can evaluate what's cosine of pi. That's going to be one of those coterminal angles. It's going to be the -1 because it's pointing into the left direction for the x-axis. So this is -1. This one we can't resolve at the moment, so we will leave it alone. And then this right here, this one we can't resolve it, but sine of pi, that's that one. It's again, the quote-unquote collapsed triangle, where there is no opposite, so this one devolves into 0. We don't care what this one is. So thus we can simplify this one into sine 5 pi over 12 with a negative. So is this optimal? No, but we can still do it. So this one itself is further what's the adjective for that? Decomposable? We could decompose it, right? So let's decompose that one. We could split the 5 into a 2 and then a 3, because 2 shares a factor with 12, and then 3 also shares a factor with the 12. And it's the 2 pi plus the 3 pi gives us the 5 pi. Alright. Wonderful, wonderful. Be careful with this minus sign. It could always lead to trouble. Let's do the expansion for this one. It's the sine function again, so copy paste the negative, but I'm going to do the brackets. Alright, now so once we deal with the negative outside the brackets, then we just treat this one as the entirety of the inside the brackets. So this is just sine with the sum, so it's going to be sine, cosine, cosine, sine, with the plus between those two. Alright, copy paste that one, simplify that one, it becomes pi over 6. And this one becomes pi over 4. Copy paste, copy paste. following algorithm. If you do it in this fashion. If you do it as sine, cosine, then make sure you stay consistent. Alright. Well, there we go. And then this one is referring to the slim angle opening up to the 1 to 2 to root 3 ratio in quadrant 1. This one is also in quadrant 1. We love those. 1 root 2. Alright. Sine 1/2. Cosine of that, root 2 over 2. Sine keeps the same sign. And then this is cosine of this one, root 3 over 2. And of course, let's just resolve that. That becomes root 6 plus root 2. I'm sure you're tired of seeing these numbers over and over again, but such is the nature of these problems, if they are to be done without the aid of a calculator. So here we go. And I think that's going to be the answer. That's doing the unfortunate strat of splitting the 17 pi over 12 into this one, which that one needs further splitting, as you can see right there. So root 6 plus root 2 over 4. Let's do it the more optimal way. You can obviously skip this if you're watching the VOD. Again, just for illustrative purposes, I chose the more inefficient route. Alright. Here we go again. We have the 17 pi. What can we split that up into? That's very nice. That's nicely divisible with, or I mean, shares a common factor with the 12. What will it be? It can be 15 and a 2, because 15 plus 2 is 17, and then 15 shares a 3 with a 12, and then 2 shares a 2 with the 12. So that's a nice split. So let's do it like that. This one simplifies, therefore, into 5 pi over 4. This one simplifies into pi over 6. Alright, so this is more optimal because, again, this is a nice angle that we're familiar with, and so is that one. Alright, same expansion for the sine function, sine, cosine, cosine, sine. This is a plus, so that's a plus. That's the first one, so 5 pi over 4. 5 pi over 4. Pi over 6. And pi over 6. And this one, where is that one for the reference? 5 is greater than 4, so we are past halfway point by this much. So that's a -1 to -1 to root 2 ratio. This one, standard quadrant 1, slim angle, opens up to 1 to 2 to root 3. Alright, reference triangles have been sketched. Let us get the evaluation. So that one is negative root 2 over 2. That one is just root 3 over 2. Uh-oh. That looks kind of bad. Let me think about this. Did something wrong happen? This is always worrisome. Okay, well, here we go. Let's continue on. It's cosine of this one. What is that? Same as this. My brain lagged a bit for a moment. Sine of pi over 6. It's 1/2. Okay, well, this looks unfortunate. This is like a negative situation. This is going to be a positive situation. So what has happened? Goodness. Alright, let's see. This is going to be negative root 6 over 4. And then this one is also denominator 4, so we can combine the top. Negative root 2. So that's a little jarring. We have this one, and then we have this one. So which of those is correct? For the sake of efficiency, I'm just going to plug this in the calculator and see what happens. I don't want to trudge through my own work. So here we go. Going on the calculator. What was it, 17 pi over 12. Let's see what we get. According to the calculator, it's supposed to be neither. Interesting. What went wrong? That's very interesting. According to the calculator. Oh, no, I'm sorry. According to the calculator, this one should be right. Yeah. Okay, I misread the negative sign. Whoops. So this is what I have on my calculator. Negative fraction 1 plus root 3 over 2 root 2. Yeah, so that should be equivalent to this one. So the first answer was wrong. All that work for the wrong answer. Well, this one you multiply top and bottom by root 2. So thus, do we get negative in the parenthetical root 2 plus root 6 all over 2 times 2, thereby simplifying into negative root 6 minus root 2 over 4. So second answer is good. First answer is wrong. Yep. Sometimes it just be like that. Okay, just to say it again. This one was the wrong answer. That one's the right answer. And the shorter method got the correct answer. Well, I mean, that should kind of make sense, right? The more steps you try to introduce into a particular problem, there's a non-zero chance the step you've introduced is wrong. So just by strictly a probability-wise perspective, more likely to produce errors with multiple steps. Which is why fewer steps is always recommended. Alright. You know what? That kind of bothers me. I do want to see the top one. What went wrong with the first one, right? So for VOD watchers, you can definitely skip this. Please skip this. This is just for sake of my sanity. Oh no, that's the correct split. We want the incorrect split, which is going to be 12 pi. I'll just reverse the order. It doesn't matter. You can add in any order you wish for arithmetic. Alright, so we got that junk, and then therefore this one simplifies into just pi. So we have the old sine, cosine. Keep the same sign. Cosine, sine. This one becomes negative 1. This one copy paste. Oh, I think I forgot to multiply the negative 1 from the first. Oh, okay, I think that's where things went wrong. I forgot to multiply the negative 1. Okay. This one becomes a 0. Yeah. Okay, so that's gone. This is what we have left over, and then we can split the 5. So that's a bracket, and then this one we can split that into 2 pi plus 3 pi. Close brackets. Don't forget this one. Yeah, I think that's what happened. Alright, so this one will split into sine, cosine, cosine, sine. So the first one is pi over 6. Second one is pi over 4. Keep the same sign. Cosine, sine. Using my standard algorithm. Again, sine, cosine, cosine, sine. Some people do it as sine, cosine, sine, cosine. Which I don't like, but who am I to tell you what not to do? Alright, so evaluating that one. It's going to be 1 to 2. And this one. Alright, so that one we're going to get 1/2 times and then root 2 over 2. Now I'm going to put the copy paste of the negative 1 in the front before I forget. Yeah, root to root 3 over 2. This one is going to be root 2 over 2. Okay, yeah, now it makes sense. Now it makes sense. This is going to be root 6 plus that one. Common denominator 4. Don't forget to copy paste the negative. And then there we go. That one is also correct. Alright. What a waste of time. That's okay. Next problem up, we have tangent of negative 105. Back to degrees. We're just mixing it up. Good old mix-ups. So if you wish, you could change this into radians if you're comfortable with radians by now, or you could just do it as degrees. So what we're aiming for again, we're aiming for the very nice degree angles, 0, 30, 45, 60, 90, and their variations. And by variations, I just mean plus pi or plus 90 degree variations. So what do we get from this one? Well, none of these have a 5 ending except for that one, right? So why not subtract the 45 from this one? What do you know? Is that a coincidence? Nope. So therefore we can split the 105 into sum of those two. So 60, I just like to put the greater one to the left for no apparent reason, and then 45 degrees. And that's the nice split. Both of those are in quadrant 1, so this should be really easy, but the algorithm for this one really is awful. It's going to be tangent of the first one. Keep the same sign because mnemonic sine is, tangent is the ratio of sine over cosine. So it follows the sine rules on the top, so you keep the same sign. And over 1, this is just memorizing the algorithm. Please have it handy or just memorize. Tangent of the 60 degrees times tangent of the 45. So here we go. We have the 60 that's in quadrant 1 as mentioned before. 60 is the wide angle, so it opens up to the root 3. Since we're dealing with only tangents, there's no need to worry about the hypotenuse. 45s. 1 to 1. Alright, so we have the root 3, and then plus 1, all over 1, minus root 3 times 1. And here we go. We're going to get root 3 plus 1 over 1 minus root 3. Not the nicest looking situation, but we should probably rationalize because that one's irrational. And the strat for this one is always just force the conjugate in order to create the difference of two squares scenario. So copy, copy, paste, paste. Flip the sign to form the conjugate. Top and bottom needs to be the same thing because we want equivalent fractions. And here we go. Following the algorithm, 1 times 1 is 1. This one times negative times positive is negative. Root 3 times root 3 is just 3. Top portion is kind of awful. It's going to be root 3 plus 1 squared. Binomial expansion, so follow your favorite algorithm for that one. I'm just going to do 3 plus, this one's root 3 squared is 3, and then I'm going to do first term times second term times 2. 1 squared. So here we go. This one simplifies into a negative 2. That's gross. That one is going to be 2 root 3, and then 3 plus 1 is 4. This is simplifiable. And it has a negative, so let's decompose the fraction. It's going to decompose into 2 root 3 over negative 2 and negative 4 over 2. This one simplifies. Cancel, cancel, cancel. And thus do we get negative 2 minus root 3. Okay, yeah, that should be correct. I miscopied the problem. The problem that I had written had a negative. So that's okay. This answer that I got is good for this positive version. But the original problem I had written was supposed to be negative. But okay, that doesn't make much of a difference though. Just affects the signage. And we should be good to go. Let me double check something real quick. Yeah. -2 minus root 3. Okay. And we're good with that particular problem. Moving on, we have the cosine problem. What do we have? It's cosine of 23 pi over 12. And standard strategy. Pay attention to the bottom. It's a 12, so we should probably split this. What can 23 split into? Let's be real. It's probably a plus. As an easier situation. So 23. We could split it into 20 and 3. That's definitely going to work. Because this one simplifies into a nice pi over 4, and this one simplifies into a okay 10 pi over 6. Well, that's further simplifiable, which further simplifies into 5 pi over what? Over 3? Yeah. Divide by 4 and divide by 4. Oh, this is perfect. This is a good situation. So again, splitting the 23 into 20 and the 3, these two decomposed fractions simplify into those ones, and that's perfect. Alright, so let's use the cosine expansion. It's going to be the cosines together. Cosine, cosine. First term of the argument and then second term of the argument. We don't keep the same sign. First term of the argument and then second term of the argument. Reference angle sketches, we have, ooh, what is this? 5 is almost twice of 3, so this is actually in quadrant 4. For the wide angle open, so it's like this. So, again, just to talk about this one will be a full 2 pi. 6 pi over 3 would be the full circle. But this is 1 short. It's 1 pi over 3 short. This is the reference angle right there. So that's how we determine if it's in quadrant 4. The ratios, we have negative root 3, positive 1 to 2. I'm dealing with that nonsense. That's default quadrant 1. Alright. Let's evaluate now. Cosine of that one is 1/2. Cosine of that one, standard. We've done this too many times. Minus opposite over hypotenuse. Be careful with the minus. This one is minus. And that one is just going to be root 2 over 2. Alright. Clean up time. We have this one. Double negative. And of course these are combinable, so therefore root 6 plus root 2 over 4. And that should be the final answer. Good to go. And we have sine going back to degrees. It's going to be 135. So this one, it ain't even a necessary situation where we have to force the sum difference identity formula for this one. We don't need to do it for this one, really. Because, what is this? Wait, do we? No, we don't. Because right here is going to be 180, and then what's 180? So this is 45 degrees short of 180. So it's like this. That's our reference triangle. So we don't even need to do the properties for this particular problem. So we can get the ratio right away. It's going to be, whoops, positive 1 to negative 1 to root 2. We don't care about this one though. So the answer is root 2 over 2. But, you know, for purposes of exercise, let's just do the split up for this one. Well, what do you think it splits into, right? It ends in a 5. So if this is a nicely designed problem, then there should be a 45 here somewhere, right? So you minus the 45, and then we get 90. So those two sum up to be that one. And those two are very nice angles. So 90 for the inner quadrant, and then 45 for the default quadrant 1. Alright, and we just need to expand this. So sine, cosine, cosine, sine. Keep the same sign. That's going to be the first one. And that's the second one. There we go. And then cosine, what's sine? Sine is interquadrant angle pointing upwards, so that one exists. But then this one is going to be collapsed triangle with the 0 adjacent. So this one is just 0. We don't even need to evaluate that, so that's gone. This one is more interesting, of course. This one's going to be 1, because it's the pointing upwards collapsed triangle with opposite congruent with the magnitude of the hypotenuse. And then this one right here, quadrant 1, very straightforward. It's going to be 1 to 1 to root 2. So referencing this one is root 2 over 2. So final cleanup step, root 2 over 2, and what do you know? Match the first answer. And we now we now have a tangent problem. Problem is tangent of, what is that? 35 pi over 12. So again, it is good form to make sure you can check to see if you can simplify the situation by getting rid of excess spins. Because doubling 12, you're going to get 24, and 35 exceeds 24. So we'll split that up, please. We're going to get tangent of 25 pi. I'm sorry, not 25, 24, because again, doubling 12 gives us 24 pi. So this one will be excess spin, one extra spin. So the smallest positive angle is going to be 11 pi. 11 pi plus 24 pi gives us back to the 35 pi, but then this one is excessive the number of spin. Therefore, these ones can this one cancels with this one, and we're left with 11 pi over 12. So just to show full work. Again, this one's just going to be extra 2 pi spin, which is 1 full rotation. And that's the most reduced positive angle. We're not interested in that one because that's excessive. So our true problem becomes tangent of 11 pi over 12. So how can we split this? Please don't do 5 and 6 because 5 doesn't share a common factor with 12, besides 1. But we don't care about 1. So what can we do? 2 and 9, that's before. Again, you'll get so used to seeing these numbers in this particular section. And 3 and 8. Those are the easiest ones off the top of my head. Can we do 4 and 7? No, we can't do 4 and 7. What other numbers are there? 1 and 10? Nope. 4 and 7. I just said that already. Nope. And then 5 and 6. Nope. 6 and 5 is just reversed. 7 and 4. Nope. So we're just getting reversals. Alright, so those are the two nicest scenarios we can get for this one. I'm sure there's some sort of minus situation you can come up with if you really wanted to. You know, let's do it. So in this one, I would probably pick that one or this one. But you can be a little extra if you wish. We can do a subtraction between something to get the 11. What could it possibly be, right? So we can have the 11 pi over 12 minus b pi over 12. And the difference between a and b is going to be 11. So what number is nice, right? It could be, what could it be? 24 and 13. No, that's awful. Ooh, that's awful. It can be 6 and no, not 6. That's definitely kind of bad, right? 6. Yeah. Oh, give me this one. Yeah, this one also works. All right. So again, I would have chosen either of those two, but if you want to be fancy smancy, you can do the 15 pi minus 4 pi over 12. And just for fun, let's pick that one. All right. So we're using the tangent algorithm for this one. It's going to be tangent. We're doing a subtraction, so just for practice, it's going to be tangent of the first one, 15 pi over 12, which simplifies into 5 pi over 4. Since this is minus, we're going to keep the minus because sign is on top, so it follows the sign form. And then we have 4 pi over 12, which simplifies into pi over 3. Alright, that's all we need for the reference. And then we have 1. Since this is minus, then we put a plus, copy paste. Copy paste. And now it's a product. Not my favorite algorithm, but you can circumvent this by just simply doing the sine over cosine. So instead of treating this like a tangent problem, you can instead change it into sine of 5 pi over 12. I'm sorry, 5 pi over 4 minus pi over 3 over cosine of 5 pi over 4 minus pi over 3. It's a little bit more work, but if you hate memorizing this monstrosity, you could just do it like this. It wastes maybe 3 to 5 more seconds. I don't know. But let's do the shorter method. So we're referencing what? This is 5. It's 1 bigger than 4, so we're in quadrant 3. It's -1 to -1. This one is going to be quadrant 1 standard. It's the 3, so it's the 60, so it's the wide angle. So root 3 to 2 to 1. So here we go. What's that? +1. What's that? Copy paste the signage first always, and then evaluate this one. There we go. That's a 1 plus. And then it's going to be this one times that one. So just multiply those two, but don't do that sign. This is where you have to be very careful. Alright. Further simplifying, we have 1 minus root 3 over 1 plus root 3. We should probably rationalize depending on teacher. Bottom portion, 1 times 1 is 1, and then Positive times negative is negative. Root 3 times root 3 is 3. Top portion is binomial expansion, so that one squared. And then this one times that one times 2. Negative times negative is positive. 3. Alright. Do we get something nice? I hope so. Alright, so we do a little bit of a sign flip. So do a flip. We're going to get root 3 minus 2. Final answer should be good. Yeah, that's good. That's the final answer. And for practice, you could always use the longer method of sine over evaluating the tangent as the sine over cosine. It's up to you. And next up we have sine. Sine of what? A whopping 374 pi. Okay, so definitely please simplify this, because doubling 12 is 24, and this greatly exceeds 24 pi on the top. So lots to take out from there. At this point, you can probably consult a calculator, but let's say you don't have a calculator. The easiest number I could see that's divisible by 12 is 360. Because 360 divided by 12, that's just going to give us, what is that going to give us, 30? So basically, that one means that we're doing 15 extra full circle spins. So that's being super, super extra. So that's the 360 degree split, but what do we have left over? We have a leftover of 360 subtracted from 374, which means we're going to have a leftover of 14 pi. Right? Yeah, 14 pi. Alright. So that looks pretty good. So this one, again, is simplifiable. It's just extra spins, so we can collapse this into nothingness. And then this one, however, that one's divisible by top and bottom divisible by 2. So we're going to get 7 pi over 6. So we don't need to do the expansion for this one. We could just simply evaluate this one, because the denominator is a nice, familiar 6. 7 exceeds 6 by 1, so we are in quadrant 3. Slim angle. So negative 1 to negative root 3 to 2. Taking the sine of that, negative 1/2. And we're done with this problem. And next up we have cosine of negative 15 degrees. So back to degrees. So 15 is not one of those nice familiar angles. It's pretty close though. It's related to a 45, right? So we have 45, we have a 30. Those are the ones we usually try to decompose degrees into. If this is not a nice degree, you try to get one of those ones, right? Etc. Alright, so we can see that the 45 minus the 30 gives us a 15, but this is a negative 15. So we need to do 30 minus 45. 5 ending is always a big clue. Alright, so decomposing the angle, we split it into this minus that. And now we just do the expansion, cosine, you keep the cosines together. So cosine 30 degrees, cosine 45 degrees. This is a minus, so you don't keep the same signs as plus. Keep the signs together. Alright, and these are very nice quadrant 1 reference angles. That makes our job much easier. And the 45, 1 root 2. Alright. So cosine root 3 over 2. Cosine of that one, root 2 over 2. Sine of that one, 1/2. Sine of 45 is root 2 over 2. Alright, here we go. Familiar face yet again. And we're good to go. And then last problem of this particular set, we have tangent. And it's going to be of negative 337 pi. And this one should feel almost like the one we did 3 problems ago. 1, 2, 3. Yeah, 3 problems ago. Again, double check the numbers. This one is a 12. This one is a 37. Doubling 12 will get us 24. This exceeds 24. So get to simplifying. So we're going to add 24 pi over 12. Because again, this one means that we're essentially we're taking away one extra spin from this one. So that is equivalent to one extra full circle spin, which is 2 pi. So let us commit to that. So negative 37 plus positive 24, that's going to simplify into negative 13 pi over 12. There we go. And we need to split the 13 because 12 is not a nice number right off the bat. So 13 splits into what? 1 and 13? Not that good. 2 and 10? That's good enough, right? Because 2 shares a factor with 12. And then 10 shares a factor with the... Wait, why did I can't do math anymore. This is a 12, this is a 13. Whoops. So that's not a good split. It's a 3. A 3 and a 10. Yeah, there you go. 3 and a 10. So we're going to have... Oh, this is a negative angle, so that makes it slightly weird, but not totally weird. So it'll be a plus. Be careful. Negative. So make sure you keep these two distinct. Since we want a negative overall angle, I'm choosing arbitrarily to do negative 3 plus, that's the signage in the middle, negative 10 to produce this one. Alright. So that's the split. Following the tangent algorithm, tangent of the first one, which is just going to be negative pi over 4. Yeah. The negative is kind of bothersome, but not super bothersome. And then, of course, copy paste the plus, not the minus. Because the minus is the second term of the argument. That one simplifies into 5 over 6. And then following the rest of the algorithm is going to be one opposite sign. This one times that one. Now, there are some properties you can exploit if you happen to know them, because tangent is going to be an odd function. You could just technically take the negative out and put it out in the front, put it out in the front. Or you could do it at this particular step. If you see a negative here, you could just take that and put it out in the front. Because tangent is something called an odd function, which we're not covering today. But if you use it, you can go ahead and abuse it. Alright. What's this? That's just going to be clockwise rotation, pi over 4. So here we go, quadrant 4. So negative 1 to positive 1 to root 2. That one. clockwise direction. 5 is 1 short of 6, so it's a slim angle in quadrant 3. -1 and -√3. So what do we got? This one. Well, that one is going to be positive. Copy paste the signage first, then evaluate. Okay, and then what do we have here? 1 minus. And then this one is just going to be this one times that one. Alright, some mistakes have been made maybe. Copy paste the top. Simplify that nastiness right there. This is absolutely wonderful. So top and bottom times 3. This one probably needs to be rationalized. Let's do it. Conjugate of this. And finally, hopefully, this one times this one is 3, and then this one times this one is -9. This term cancels with that term, and then following binomial expansion, that one squared is 3, this one times 2. And then this one squared is +9. Further simplifying into what? 12 minus 6 √3 over -6. Everything is divisible. All 3 terms are divisible by 6, -6. So I'm going to divide by -6 all around. So I'll divide by -6 is +√3. Divide by -6 is -2. Divide by -6 is +1. So this should be the final answer. Okay. And then finally we can move on to a different type of problem. Ultimately though, they're pretty much the same thing. We're going to have the cosine as a given. This is going to be given information. What are we given? We are given cosine of alpha is equal to 1/2, and then we are informed that alpha is an angle that's wedged between what? -π and 0. So we have domain restrictions. That just basically helps you narrow down which reference triangle to use, because if we don't have this one, there are two main situations that can arise that will give us an adjacent of 1 over hypotenuse of 2. So basically, it could be quadrant 1, or it could be in quadrant 4. So the only difference being the opposite, which is √3 or -√3. But since we have domain restrictions, we know it's restricted to what? It's only restricted from 0 to -π. And the one that we drew that matched this restriction is the one in quadrant 3. I'm sorry, not quadrant 3. It's a positive adjacent. I'm sorry. It's positive adjacent 1 over √2. Hypotenuse 2. So we have a negative opposite right there. So from this clue, we can generate 2 reference triangle, but from this additional clue, we know it's going to be in quadrant 4, not quadrant 1. Alright, and then that's going to be the 2 clues for the alpha, and then we have a clue for beta. Given sine of beta is equal to √2 over 2. So again, just by having this one alone, it's the ambiguous situation, technically infinite. But if we're chasing down the smallest positive angles, reference angles, what do we get? That's going to be positive 1 opposite over root 2 adjacent hypotenuse. So either in quadrant 1 or in quadrant 2. The difference being the sign on the adjacent. The positive negative on the adjacent. So it's either this angle or this one. But we are given a domain restriction, which is from 0 to pi. Alright. 0 to pi, so basically from here to here, so both triangles are still going to be an option. So I'm going to change this problem just a little bit. Otherwise we have to deal with 2 different scenarios, and I don't want to do that. So changing the domain restrictions, let's change it from negative pi over 2 to positive pi over 2. So we're stuck to the side, so not this one, with this new changed domain restriction. Alright. So this is all just given information. So we're given information on alpha, and then we're given information on beta. Now here comes the question. The question is, evaluate this. Of course. So we're just doing some more expansions. This is just a different type of problem, but the underlying theme is the same. We're just doing some difference expansion. So sine function with a plus. So sine, cosine, cosine, sine. Sine, cosine, keep the same sign. Cosine, sine. And of course we already sketched out the handy dandy reference triangles. We're referencing this one and that one. So sine of that, negative root 3 over 2, and then cosine of this one, cosine of back to that, and then sine of that nonsense. Looking good, and then therefore we could change this into root 2 minus root 6 over 4. And we're done. So slight variation of a problem, and not radically different, honestly. And next up, given information, tangent of alpha equals negative 1. Domain restriction, pi over 2, or rather alpha is between pi over 2 and 3 pi over 2. So given information number 1 and then given information number 2. Cosine of beta is equal to negative 1. I hope you recognize this scenario. And then we're asked to evaluate sine of alpha minus beta. So we need the reference angles in particular. So tangent, this one you can think about it as negative 1 over 1 or 1 over negative 1. So let's see. So for this one, we have here. So that could be a negative opposite over positive adjacent. So here, quadrant 4 with the 45, 45, 90. Or we can have where positive opposite to same magnitude negative adjacent. And we do have domain restrictions. It's from pi, which is the interquadrant angle, to 3 pi over 2. So from here to there. So this, we're ignoring that one. We're done with the reference angle for tangent of alpha. Alpha, I mean. Now we work with this one. This is beta. This is what this is a cosine function. Therefore, we have a matching adjacent to hypotenuse in terms of magnitude. So we know this is an interquadrant angle because the adjacent has the same magnitude as the hypotenuse, but it's a negative, so it's going to be this collapsed triangle situation. And there we go. So can we evaluate this one now? Yes, we can, because now we have the proper reference triangles, quote-unquote triangle here. Do the expansion. So we have sine, cosine, cosine, sine. Keep the same sign. So what's the alpha? It's going to be this one, which is from here to there, which is 3 pi over 4. So evaluating this one, for the sine, root 2 over 2. Cosine on the beta, wait, what am I saying? Whoops. Why am I writing the ratios here? I should not write the ratios. I'm going to put the angles. So I kind of just jumped ahead. So this one is that. And this one is that one. Copy paste. Cosine of alpha is this one. Don't forget the negative sign. Sine of beta, that's basically this one. This is a collapsed triangle with a 0 opposite, so this whole thing is 0. So final answer, negative root 2 over 2. Should be good. Alright, next up for the same type of problem. Given information is sine of alpha. That is equal to root 3 over 2. And we have a domain restriction. Here to there. So, domain restrictions first. It's from interquadrant angle here to interquadrant angle there. We need a positive opposite, so it's in quadrant 2. Adjacent is negative 1. So thus the reference angle is right there. Yes. So this one is alpha from here to there. We don't need to know exactly what it is. We don't care. Alright, so that's the first piece of information, and then the second piece of information given is... I should have written this first. Yeah, I'm just doing the problem like midway. And the question asks to evaluate tangent of alpha plus beta. So just to pretend we're starting off from a fresh, here's the problem. There's the problem. We have given number 1, and then we have given number 2, and we're asked to evaluate that thing. And then again, from the first 2 pieces of information, we can generate this situation. It's the 30, 60, 90 in the second quadrant. And then from this piece of information, that one's a little more annoying to deal with. Let's do the quadrant restriction first. So it's from pi to 2 pi. So it's either, whatever angle this is in, it's going to be in either quadrant 3 or quadrant 4. we need the negatives to not cancel out. So it can't be in this situation because that's negative adjacent and negative adjacent and negative opposite. But this one has a negative sign. So that means this angle B, angle beta, must be in quadrant 4. And in quadrant 4, the opposite is negative, so this one has to be negative. And the adjacent is positive 1. Yeah. Alright. Let's evaluate this situation. We're doing the tangent expansion. That's a plus. So tangent alpha plus tangent beta all over 1 minus tangent alpha times tangent beta. And then doing the evaluation, tangent of alpha, this one's alpha, so tangent is root 3 over negative 1. So negative root 3. Evaluating tangent beta, that's going to be opposite over adjacent. But do the signage first. Then evaluate. One minus this one times that one. So the negatives will cancel, and the square root function will cancel, and we'll be left with just the 3. Cleanup step. Those are combinable. Those ones are combinable. Negative 2 cancels with negative 2. Final answer is root 3. And then last problem for this particular set. Given information, we have tangent of alpha equals 0. Domain restriction, negative pi to negative pi over 2 to pi over 2. So that's first given and then second given. Tangent of beta is equal to what? Root 3 over 3. Restriction, that's opposite over adjacent. It doesn't have to be 1, I'm just making it 1. So it's like the collapsed triangle situation where the opposite is 0. So the height of the triangle is 0. So it's either going to be in this interquadrant or it's going to be this interquadrant. But we do have domain restrictions. So it's only from negative pi over 2 to positive pi over 2. So not that one. We're dealing with this interquadrant angle right there. Alright, sure. This one, what are we doing here? That's kind of annoying, right? I'm going to change this back to irrational denominator. So 1 over 3, or it could be negative 1 over negative root 3. But domain restrictions. So we're going from pi over 2 interquadrant here to 3 pi over 2 interquadrant there. We're dealing specifically with the tangent, so we need both signs to be the same. This one is in quadrant 1. We already rolled that out from the domain restrictions. So it must be in quadrant 3. So that's going to be a negative root 3 and then a negative 1 kind of situation. Yeah. Okay. Now that we've sketched out the reference one, this one is positive x direction, so the adjacent over hypotenuse is positive 1. Okay. What are we doing again? Oh, sine. Sine, cosine, cosine, sine. Keep that negative. Start slam dunking those values in. So what's sine of alpha? Which one's alpha? This one? Yeah. I think it's that one. Yeah, it's that one. So sine 1, this is a collapsed triangle. It's the opposite that is collapsed, so that's 0. So this part is 0. We don't care what this one is. As long as it's a discrete value. And here, don't forget the negative. We have cosine of alpha, which is 1. And then times sine of alpha. Wait, this would be beta. Whoops. Almost messed up the algorithm. Sine, cosine, cosine, sine. Yes. Sine of beta. This one's beta. It's going to be negative 1 over 2. 2 negatives cancel out, and then 1 times 1/2 is just 1/2. Final answer. And that should be good. Alright, pretty good progress. So we're pretty much done with that particular type of problem. It's referred to as the sum difference identities, I think. Did I have a note here somewhere? Nope. No, I don't. That's unfortunate. Alright, so that's kind of quote-unquote going forwards, and then that was kind of going forwards and backwards. That's kind of. And then now we're going to do strictly backwards. Just to reiterate what that means, we've been going forward. So given something like this, we were given something like this, where we just have one nice angle, but then we split that angle into alpha plus beta. And then starting from here, we expand it out using the sum difference formula. So sine, cosine, cosine, sine. So that's going forwards, right? And now we're going to go backwards. So starting from this nastiness, starting from the expanded form, we are going to contract it into the smaller situation. So we're now starting with the bad numbers in the expanded form rather than the other way around. So here we go. It's not a particularly big deal. I think I did this on the last stream, but too bad. You see it again. It's going to be sine of pi over 12. You know what? Let's change the problem. So I think I already did this problem last time, so let's do the negative instead. So we have sine of negative pi over 12 times cosine of 5 pi over 12 and we have a subtraction between those two, and then cosine of negative pi over 12 times sine of 5 pi over 12. So expanded form, we're going to contract this one into a singular thing, but take a quick evaluation. If we call this one alpha, this is a negative pi over 12, this is the one matches it, so that's the alpha. This is the 5 pi over 12, which matches that one, so we'll call that one the beta. So having some semblance of order, this is going to be the alternation of sine, cosine, cosine, sine. So we know we're contracting this into the sine type function. This one starts first from left to right, Western style reading, and then this is beta second. Sine function keeps the same sign. So that's the plan of attack. We're going to change this one into that one. But just double check that the numbers are actually nice. So if we subtract this one using this one, will we get a nice angle that's we are able to evaluate? Check real quick. So alpha is pi over 12, and then this beta one here is 5 pi over 12. So minus that one. which is going to result in 6 pi over 12, which is simplifiable into an interquadrant angle. That's going to be negative pi over 2. Yep. That has a denominator we are familiar with, so this is a good root to take. So let us execute this root. Well, technically the work is already essentially done, so that serves a dual purpose of taking a survey, and if it works, then you can continue on by just putting this into the sine function. Alright, so just to retrace the steps, we have this expanded form with a subtraction in between them. We have the alternation of trig. The cosine is not with the cosine there, so we know this is going to be a trig, some sort of variation of a trig of a sine function. So this is going to be a minus between the two angles, and since this one matches this and then that matches that, everything is perfectly lined up. So let me start to colorize. That's for some visual clarity, I hope. Alright, so again, we just simply recognize the situation, going backwards, and then we merge the two angles to get this nice angle right here. That's an interquadrant angle. This is the one that goes downwards. This is neutral, 0 degrees. We're going to subtract pi over 2, which is going from here to there. And thus we end up at this interquadrant angle. It's the one pointing downwards. So the opposite to hypotenuse is -1, and then the adjacent is 0. But we're just doing sine. So that's when the magnitude of the opposite is equal to the magnitude of the hypotenuse. But since it goes downwards, negative. And that's the answer for this problem. Good to go. And then next up we have the cosine. Cosine of what? 5 pi over 24? And see what's next to it. What's next to it? It's cosine. So this is already indicative of which direction to take it. Oh, that's not a 2 pi, I'm sorry. That's a 24. But the prior observation still stands. And then we have a subtraction. Do be careful. Don't just auto-assume that this is going to be alpha. Make sure that the numbers are harmonious. So this one matches that one, so we can call that one alpha. And this one matches that one, so we can call that one beta. From left to right, following conventions. There's a subtraction in the middle, but keep in mind it's the cosines are cooperating. So we are dealing with a cosine condensation situation. So just take argument number 1, that's the alpha. And then we're going to add it, because again, this is minus, it becomes the plus, because this one is a cosine, not sine. And just make sure that the numbers add up to be something that's workable. So 5 plus 11 is 16 pi over 24. Top and bottom divisible by 8. So therefore 2 pi over 3. That's perfect. That's something we are familiar with. What is the reference triangle? 2 is 1 short from 3, so it's going to be in quadrant 2. The 3 is a wide angle. So this from here to there is 2 pi over 3. Ratios. Root 3 to -1 to +2. Cosine, -1 over 2. And then we're done with that particular problem. Good to go. And the next one up, try to think about which trig function it is just by looking at the groupings. See what's next to it. Take an educated guess about which one this is. Did you get it? It's the sine that is paired up with the cosine, so the cosines are separated, so we know this is going to be a sine trig function. And double check to make sure all the numbers match up. This one clearly matches with that one, and then this one matches with that one, so this is a valid situation. Some teachers can try to trick you by putting something else, like a 2 pi over 16 or something, and this one's going to be distinct. And then here, this would be inapplicable. You can't use the condensation rule unless this is somehow coterminal with this one. So be careful. Be very, very careful. But no tricks here. It's a pretty straightforward. This one matches this one, and then this one matches that one perfectly. If I wanted to be extra goofy, I would have. Again, if I wanted to be extra goofy, I could do, what is this? 16 times 2 is 32. 32 plus 5. I could change this to like a 37 pi, just to try to trick. See how those are different? But this one is simplifiable into 5 pi. But again, no tricks here. This is a plus, so we're going to be adding those two arguments together. Sine keeps the same sign. Is that a nice situation? Well, 5 plus 7 is 12, and that is simplifiable with the 16, so we're good to go. Divide by 4, divide by 4. This one feels familiar, right? I think we just did it. Alright. Which quadrant are we in? Oh no, I'm sorry, this is similar to the previous one. So 3 is 1 short from the 4, so we're in quadrant 2. This is going to be the 45, 45, 90, so positive 1 to negative 1 to root 2. Okay, taking the sign of that, that's just 1 over root 2. And we're done with the problem. So these ones aren't too bad. It's just pattern recognition. Like a lot of early math, right? Next up we have tangent, of course. We have tangent of 5 pi over 12. We have a minus. All over 1 plus this one times this one, right? There we go. So we're just basically condensating this. We have a subtraction. This is with the tangent. Don't forget, tangent is the ratio between sine and cosine of the same angle. This is going to be a recurring property. It shows up quite a bit. Alright. Just make sure everything is in valid form. So this one is 5 pi over 12. It matches 5 pi over 12. This one is pi over 12. It matches pi over 12. This sign is opposite of that sign, so this is a valid situation. We can therefore transform it, condensate it into the nice clean tangent, singular tangent. The minus is on top. So the minus goes into here. So angle number 1 minus angle number 2 for the condensation. Alright, and then that one turns into a very clean 4 pi over 12, which is a very clean pi over 3. And that's what we're evaluating. Tangent of pi over 3. That's a very pleasant, well, what is that? Quadrant 1 angle, yes. So it's a wide angle, it's a 3 one, so it opens up into the root 3. And 1 to 2. We're doing tangent, so that's opposite over adjacent. So root 3, we're done. Alright, mowing these problems down. Wonderful. And another problem we have here is going to be sine of 11 pi over 21. New denominator, right? It's not just 12 anymore. See that? Finally get some different numbers. At least from first glance. Try to hypothesize what this one's going to be. See, I'm pulling some tricks here. Alright, so multiple nonsense going on. Well, first things first, you notice that the sign comes first. Some people, if you're not paying attention, they automatically default to sine, but it's not. Look what's paired up with the sign. It's also a sine. Cosine is paired up with the other cosine. So this is actually cosine condensation. So watch out for tricks. And of course, looking at the arguments, well, this one is 11 pi over 21. Neither of those two is 11 pi over 21, at least from first glance. So let's check this out. This one, can we simplify it? No, 11 is prime, and then 21 doesn't share any factors with 11. And doubling the 21 is 42. That is less than 42, so this one, not much to do with this one. That one, not much to do with this one. This one, however, if you double 21, it's 42. This one exceeds 42. So let us perform the subtraction. Again, 42, we're just removing one full circle rotation because double that one is 42 pi. If you subtract, oh, that's weird. If you subtract those two, it's going to be 11, which not coincidentally matches that one. So this is just a visual trick. It's just 11 pi over 21. And this one's another visual trick. This one is a positive small angle. This one is a negative situation. So we can just transform this one into a positive angle and check to see if it matches this one. So if you double the 7, that's 14. So all you need to do is add 14 to get to the coterminal angle. So 14 pi over 7, because again, this one is 2 pi, which is one full extra rotation, which leads to coterminal angles. That one thus simplifies into pi over 7. And of course it matches in the end. So we know this is going to be a valid situation. So checking out again, we know that we now see that the argument angle number 1 is 11 pi over 21, which matches this one. We see that the pi over 7 now matches the pi over 7. The cosine functions are together, so we know this is the cosine. This is a positive, so we know it changes into a subtraction between those two angle arguments inside the trig function. That's cosine. So cosine of angle number 1 minus angle number 2. Oh, okay, well, this is a 21, so we need to up that one. So times 3, and then times 3. And is that combinable? Yes, it is. We're going to get cosine of... Oh, this might not be a nice situation. We're going to get the negative 8 pi over 21, which unfortunately means I've miswritten the problem. But everything I told you up to this point is still true. Alright? So this is technically the correct situation, but it is not a nice situation. So what I'm going to do is I'm going to change the problem just a little bit. I'm going to change this one to a plus. I mean to a minus. Because I want this, yeah. I want that to be. I want this sign here to be plus. And the reason why I want it to be a plus is because that one's going to end up being 14 instead of this awkward 8. Yeah, so that's what I'm going to do. I'm going to change the problem. So VOD watchers, well, I'll give you the timestamp for this one. But again, everything I said up to this point is still going to hold true. So let me just change this problem. It needs to be a minus. So let us reverse time. Yeah, do I want to do the full thing? Let me think about this. You know what? Yeah. It's okay. I'll just timestamp this correctly. Let me change this real quick. What was that? It was a 42, so 53 pi over 21. And then the second one was a negative 13 pi over 7. So, starting over again, here we are. This is the first time you've seen the problem. We're going to make a few observations. Don't fall for this trick. If you see sine right away, it doesn't mean that you're going to go straight to a sine function for the condensation. Because that is if someone's being particularly tricky, someone could put this one first, right? Oh, no, I remember now. Okay, actually the previous situation was correct. It does need to be a plus. Okay, good. Alright. Take 3. Third time's the charm, right? But let me beautify this real quick. Alright. Okay, so all the work was actually correct before. I just didn't realize something. This order of these... The ordering is actually relevant in this situation. Alright. So let us begin again. So take 3. Make a few observations. Most people, if they're not careful, they will see this sine one and they will auto default into the sine, thinking it's a sine condensation, but it is not. Because the sine here is paired up with the sine, and the cosine is paired up with the cosine. So this is actually a cosine function. So note number 1. Note number 2, none of these angles apparently seem to match up, at least in the beginning, right? So we probably have to perform some sort of simplifications just to double check. And then number 3, we make note that the ordering is off, right? So therein lies some other trick to the situation. So what do we do in this, given this situation? We actually might have to change the sign after all. Yeah, I think we have to change the sign. Yeah, unfortunately. I think we need to change it. Okay, well, I guess this is take 4. Yeah, because I don't think it's gonna work if it's a plus, because the ordering, the fact that it got swapped is important to the situation. Okay, so final take, final take. Promise. All right, here we go. So this is the first time we've seen the problem. We're looking at this. Don't be fooled into thinking this is going to be a sine condensation, because the sine is with the sine. The cosine is with the cosine. So this is actually a cosine condensation. Alright. Thing number 2. We make note that the angles all appear to be mismatched. So there's some sort of simplification tricks going on. We probably need to simplify. Thing number 2, the ordering is kind of weird because we have a minus. We're used to seeing something like cosine alpha times cosine beta plus or minus sine alpha sine beta. So that's what we're used to seeing. We're used to seeing this sort of situation where the cosine, if it is a negative situation, which in this case it is, then the cosine pair is supposed to come first from left to right, but lo and behold, it's on the right. So we have a few tasks to resolve, to take care of. Let's first check to see if the angles are actually the same. Does this one match this one, or does this one match that one? Well, this probably matches this one, right? Well, you can see that the 11 here does not exceed twice 21, but this 53 does exceed twice 21. So this one is has a coterminal angle that's smaller. So let us simplify this one. Doubling the 21 is a 42, and we're going to subtract that from the 53. So 5 minus 4 is 1, 3 minus 2 is 1, so that's 11. So this one simplifies indeed into that one. This one is small. It's going to be positive 1 over positive 7. Not much to do here, but this one is a negative angle. Let's bring it up to positive by adding 1 full rotation. And 1 full rotation is 2 pi. But we need to match the denominator, so that's plus 14 pi over 7. And that one, of course, reduces to that. So perfect. So now we see that the arguments are indeed matched up. So this one matches this one, and then this second argument matches second argument. So, however, this is going to be wrong. Don't put 11 pi over 21 minus 11 pi over 7, because this negative here is actually throwing things off. Cosine pair comes first. So what that means for us is we need to group these together and then factor a negative from both term number 1 and term number 2 just to switch the order so it matches this one. Do I want to show the full work? Yeah, let's show the full work. So it becomes this one. So now that one matches regular form, and then the negative becomes positive, but then the positive becomes negative. So now this is like in standard form of sorts. Okay, and then we have that sort of situation, and now let's get to seeing what happens if we do what? That's a minus. This is a cosine condensation, so the minus changes into a plus. Argument number 1. Argument number 2. Don't forget the old negative on the outside. Alright. There we are. Let's just make sure the summates to be something very nice. So this one is actually going to be times 3. Times 3. The 3 plus the 11 is something indeed nice because it's 14 pi over 21. This one is simplifiable. We can divide top and bottom by 7, so divide by 7 is 2, divide by 7 is 3. So our true problem thus becomes negative cosine of 2 pi over 3 with a negative. And just sketch out the reference triangle. 2 is 1 less than 3, so we are in quadrant 2, and then it's going to be the wide angle into the root 3. Adjacent is negative 1, hypotenuse is 2 Rachel. We're doing cosine. So, negative 1 over 2. And we are finally finished with this particular problem. First try, right? First try. Alright. Let me consider a few things. Actually, I think I'm just going to call it for the day. I think dinner is calling. So, probably do some more of these type of problems. Probably revisit the first two problems yet again, and then we're going to introduce the ones with the algebra, where they're going to be the unknown x values inside the trig functions. So that's going to be some fun stuff to deal with. And then we're going to do the last property of this particular section. It's going to be the, what is it? The, I forgot what these are called. But there's going to be a final formula to reference. It's the, what was it? Sum to product. Oh yeah, it's something called the sum to product rule, or difference to product. But don't worry, we're going to cover that in the next stream. But for now, that's going to be it. There's a slight chance there's a very, very slight chance. Probably, no, I'm probably not going to stream later. That's probably going to be it for now. I hope you have a good one, and I'll see you in the next one.